all right. So if you look at this function right here, you could solve it for y. You could take, you would have to take the inverse sine of both sides. That's what you'd have to do. But the nice thing about implicit differentiation is you don't have to do that. You just differentiate it without solving it for y. So let's go ahead and go through this. We did several of these. We're going to get into the ones that are a little bit more complex today and then do maybe just a few applications. So let's start on this like you always do. You just take the derivative of both sides of the equation with respect to x. That's a real key. And the Leibniz notation is the ideal notation to use on this then. And then there's one key thing that you got to remember, okay? Okay, so here's the deal. Okay, what is the derivative of a sine? What's that rule? Cosine, all right? So you go ahead and say cosine of y, the same variable, but what we said is these variables do not match. So what we're really doing is the derivative of y, okay, which is 1, but then we say dy over dx. That's the key thing. If the variables don't match, x and y, then you have to put that dy over dx, because that's ultimately what you're trying to find. You got to solve the equation for that. Okay, then we go to the right side. What's the derivative of the right side? 20x to the third, right, good. Okay, now see that the variables do match there, so that's just kind of a normal derivative like we're used to doing. And of course we know the derivative of 5 is 0, okay? So then that means all we have to do on this problem is we got to solve this equation for dy over dx. So how do you accomplish that? You divide by the cosine, right? Okay, so what you need to do now is just go ahead and divide by the cosine, and then we have the answer. So this is what the derivative is. Notice that it has both an x and a y in it, so that would be 20x to the third over cosine y. Okay, so that's the first thing that we were talking about, is that's how you do implicit differentiation. Don't solve your equation for y, just differentiate. Okay, does that make sense? That's actually an easy one. Okay, all right. Now what we're going to do is the derivative we know gives a slope of a tangent line at any point on the curve. And what would happen with this one is we just take this derivative, 20x to the third over cosine of y, and we just plug stuff in. That's another nice thing about implicit differentiation. You just plug the variables in, and then we'll get the slope. So x is going to be 1, so that's going to be 20 times 1 to the third. And then we're going to do cosine of pi like that, okay, and work that out, okay? All right, well, you got to go back to the unit circle. You do that all the time in calculus. So at pi, what's the value of the cosine of pi? -1, right? Okay, because that's the x value. So what looks like you're going to get 20 over -1, so that's -20. So that what that means is this curve, and that curve could be graphed. It's actually not a function. I don't know what it would look like, but it would be some sort of a loop or something, and that would be the slope of the curve of the tangent line at the point 1 pi. Okay, like that. All right, does that make sense to everybody? That's not too hard of a problem. They're going to get kind of a little heavier today as we go through these. Okay, any questions about anything? Okay, let's go through this one. So we're going to kind of continue to do the same thing. Most of this section is practicing the skill of implicit differentiation. So we're going to start by doing the derivative of both sides. Okay, you don't solve for x or y. So we just do this, and we do this to both sides like that. All right, okay, now you got to watch real carefully when you do this now, because the chain rule, the chain rule is super important. So what is the rule for the derivative of the tangent? Which one is that? Secant squared, right? Okay, so what we do is we write down secant squared of xy. Okay, that's part 1. Okay, however, the chain rule says also do the derivative of that function inside, right? This is not just a secant of x, or the tangent of x, it's tangent of xy. So what you got to do now is you got to apply the chain rule. So now I'm just going to write this as the derivative of xy, then we'll deal with it in the next step of the problem. Okay, like that. That's chain rule, all right? Okay, now let's go to this side. What's the derivative of x? 1. What's the derivative of y? You got to be careful. dy over dx, good. Okay, see those variables do not match. So the derivative of y is 1, but then you got to do the chain rule is really dy over dx like that. Okay, so we got that, all right? So now what that means that we need to focus on is we need to focus on this derivative right here. Okay, how are you going to differentiate x times y? What rule applies? Product rule, exactly, good. So we have to use the product rule. So you're going to have secant squared of xy. Now let's draw like a bracket, and now you got to apply the product rule. Okay, so we got the first is x. Okay, then you're going to do the derivative of the second. What's the derivative of y? dy, it's 1 dy over dx. Okay, variables don't match, so it's dy over dx. Okay, good. Now you go backwards. Second is y. What's the derivative of x? 1. Okay, there we go. Okay, so that's your product rule. So again, I did first derivative of second plus second times derivative of first. Everybody okay there? Okay. And then the right side is going to just be 1 plus dy over dx. So we've actually done our derivative now. Okay, our derivative is done. But what we have to do next is we have to focus on the algebra of solving this equation for dy over dx. Okay, so the way you would want to do this is you would pretty well be forced to do a distributive property here, and you'd be forced to multiply this thing through that bracket. So we need to go ahead and do that. All right, so let's go ahead and do that then. So we're going to have, I'm going to do this like this now. I'm going to put x times dy over dx times the secant squared of xy, like that. Then I'm going to have secant squared xy times y. Doesn't really matter what order you put stuff in. What I try to do is I try to get students in the habit of putting stuff in front of a trig function because it's a little bit less ambiguous. So I did a distributive property, so I got that. Now I've got this. Okay, now the whole focus of this problem still is somehow we got to solve this equation for dy over dx. Okay, everybody with me? Okay, now the only way you're going to do that is everything that has a dy over dx needs to go to the left side. Any expression that doesn't needs to go the other side, so you want to rearrange this in your head. This thing right here needs to move. This thing right here needs to move. Okay, so if you do that, what you're going to have is x times dy over dx times the secant squared of xy. Okay, that's going to stay where it is because it has a dy over dx. Move this dy over dx and change the sign when you do that. Be careful about that. Okay, so that takes care of that. So those two things are now in their correct place. The 1 needs to be left where it is. And then move this y secant squared of xy to the other side. Okay, like that. So it's all about rearranging. Everything that has a dy dx goes to one side, everything else goes to the other side. All right, now what do you do from here? You factor, exactly. A lot of times students get here and they get stuck. Okay, you're going to factor all the time on these things. So see, this is a common factor, so you just pull that out. So you would have dy over dx, and then you would have this. What would be left over after you take that out would just be this stuff. Okay, there would be a 1 left over there. So you would have x secant squared xy minus 1, like that. Okay, and then this side would just stay the same. And then one more step, and we are done. What's the last step? Yeah, divide by all that, right? Okay, you're trying to get dy over dx by itself. This is a factor that's multiplied by that. And so what we do now is we just divide both sides by x secant squared xy minus 1. You can do that step in your head, too. You don't have to necessarily show this step. You can just write the answer if you want to. Okay, so it looks like what we have is we have dy over dx. After that crosses out, looks like what we have is 1 minus y secant squared xy, and then x secant squared xy minus 1, like that. That appears to be what you should get on that then. Okay, now I think as I was looking at my answer key, and I may have on my notes, I think I had that thing, I had both things backwards for whatever reason, but it doesn't make any difference. That's a fine answer right there. Okay, so that would be where we stop. I don't really see any simplification. Why could you not cross out the secant squared xy? I see that all the time in this class.
Still two terms.
This minus sign right there keeps you from doing that, right? And you got one there too. You can't do that. So the only thing you could possibly do is try to see if there's any factoring, but there isn't any. That's it. So we're done. Okay? All right? So any question about that? That's a harder one, I think. What do you think? Okay? They get a little bit messier as you go through this, and these are the ones that sometimes students have a little bit more issues with. So we're going to do a few more like this. Okay, now what we're going to do is the slope of the tangent line at 0, 0. Okay, so that's nice that we have zeros. So we just have, that just means that x is 0, y is 0. So we're going to go to this expression, and we're just going to replace x and y with 0. Okay, so if we do that, a lot of times I write the notation like this, dy over dx at 0, 0. You see that notation a lot in Leibniz notation. That just means that's the derivative evaluated at that point. Okay, so let's plug it in, see what we got. Looks like we have 1 minus 0 times secant squared of 0 times 0. There's some things you can do in your head on this, which is fine. And this is great the way this is working out. I'm glad I gave you zeros on this one. Okay, so we got that. And then we'll kind of see what we're left over with then. Okay, so here's what I see. That goes to 0. That whole thing does. That whole thing goes to 0 because you're multiplying by 0. So it looks like we're going to be left with a 1 over negative 1. So the slope of the tangent line at 0, 0 would be negative 1, like that, okay? With pretty good computer software, you could actually graph tangent xy equals x plus y. It's probably not a function. I have no idea what it looks like, but it's probably would fail the vertical line test. That's what happens on a lot of these problems if they don't solve for y. Not always, but a lot of times. Okay, is there anything that I need to clarify there? The key thing is the chain rule. That shows up in these more complex ones, and you have to deal with that the correct way. All right? Okay, so let's go ahead and do one other one like that, and that's got a chain rule in it. And this one's got quite a bit going on it too, I think. Okay, so let's kind of run through this one now. So start off the same way. We're going to do derivative of xy plus 1 to the third, and then we'll do the derivative of x minus y to the second plus 8 like that. Okay? All right. So the idea with this is, remember, this is a chain rule right here. The big function is what? Something to the third power, right? So if you do that, you're going to bring the 3 down, second power multiplied by the derivative of what's inside. That's a chain rule going on there. So you approach this like this. Bring the 3 down, leave that alone, second power. That's not it, though. Then you got to multiply by the derivative of what's inside. That function there is xy plus 1 like that. So we'll go to the next step and we'll finish that up. Okay, right side's real easy. Make sure everybody's got this. Derivative of x, what's that? 1. Next one, derivative of y squared. 2y dy dx, right? Variables don't match. So be careful about that. That's 2y. But you put the dy over dx like that. Derivative of 8's nothing. There we go. All right. So now that shifts our focus to this. So we got to work that derivative out. So I'm going to bring this down. That's 3xy plus 1 to the second. Okay. This is a product rule again. We did this a minute ago. So the first is x, the second is y. That's a product rule. So you got to do that like this. So it's going to go like this. You have the first. The derivative of y is what? dy over dx, right? Okay, backwards. Y, derivative of x, is just 1, right? Okay, and then the derivative of 1, since that's a constant, is 0. I'll go ahead and put that in like that. And then the right side is going to give you that. Okay, derivative is pretty well done. All right, so is there any questions about that? Okay, the chain rule is the most complicated part of that. And inside of that chain rule, there's a product rule in there. Okay, so you're kind of now beginning to put all these rules together. So let's see what we have. This is going to be 3xy plus 1 to the second. Inside the parenthesis, I've got x times dy over dx plus 1 or plus y. Then I got 1 minus 2y times dy over dx. So now the goal is, now we're to the algebra stage, is we got to get all the dy dx's on one side, everything else the other side, and then solve. Okay? The only way you're going to really accomplish this now is to distribute that whole thing through that parenthesis right there. You got to do that first. Okay, so when you do this, you're going to have, I'm going to write this as x times dy over dx times 3xy plus 1 to the second, like that. You pick the order you put that in. That's just the order I'm going to choose to do it in. And then this one I'm going to write like 3y. That was a y, right? So that's 3y xy plus 1 to the second. Okay, so that's distributed. And then this side you're going to have 1 minus 2y times dy over dx like that. All right?
Where'd you get that first x from?
The first x from? Which x are you talking about? This one?
Yeah.
That one?
Yeah.
Okay, it came from here. You can start getting these big expressions that came from here. I did this. I got the 3x right there. Okay, then I've got the xy, then I got the dy dx. I'm doing a distributive property, so I'm multiplying that whole thing, then I'm multiplying that whole thing. You see?
So you're doing 3 times the xy?
Yeah, right here.
Okay.
See, I'm doing a distributive property. Okay, inside that. So I got a 3, I got an x, I got a dy over dx,
Oh, okay.
and I got that. Okay? It doesn't matter what order you put it in. I just put it in that order. Okay? Doesn't make any difference. Okay, so now what I'm going to do is this. Let's see. What do we need to move? This whole thing needs to move, right? Because it's got a dy over dx. This whole thing right here also has to move because it doesn't have a dy over dx. Okay, so what you're going to have is this. You'll have, let's write that now as 3x. Looks a little bit better if we do it this way. So I'm going to write that as 3x. And then I'm going to do xy plus 1 to the second times dy over dx. Okay, this thing moves, so that minus 2y is now going to become plus 2y times dy over dx. Okay, and the right side, I've still got the 1. That stays. And then this thing right here is going to move. So that plus now changes to minus 3y times xy plus 1 to the second, like that. Okay? And you're going to kind of see that these things always finish up just about the same way. What are you going to do now? Factor, right? That's the purpose, okay? You got 2 dy dx's, take it out, factor it. Okay, so that when you take that out, you're going to have dy dx, so I'm going to have a bracket, 3x, xy plus 1 to the second, plus 2y, that takes care of that. Then the last step, you can always do that last step in your head. You don't have to show it, because now what you're going to do is divide by this whole thing right here. So you just divide by that, and then you can write your answer. Okay, do that in your head. Okay, so let's just write the answer now. We have dy over dx. Got the right side is 1 minus 3y xy plus 1 to the second, all over this mess. So that's 3x, xy plus 1 to the second, plus 2y, like that. Okay, let me ask this question. I keep asking this throughout the semester because I try to get students to get this down. Could you cross out the xy plus 1 to the second? No. How come? Because of that, and because of that. Okay, be careful. All right, please, promise me you won't do that stuff. All right? All right, very good. Okay, you guys follow what I did on that, okay? All right, okay. Okay, let's see. There's a couple of applications that I want to look at on here just a little bit. And what you get into a lot of times in implicit differentiation, like for instance, this thing right here, you can use some pretty advanced software to graph stuff. If you put this in your TI doesn't do stuff like this. I think a TI-89 will, and that would be the graph of that. Almost looks like an apple, kind of, doesn't it? So the idea with this is when you're doing implicit differentiation, you're actually finding a slope of a tangent line somewhere on that curve, but it's not a function. Okay, it just looks like that. When you start getting into Calculus 3, if you're going to take that class, you start looking at three-dimensional things, and you start looking at planes that are tangential to three-dimensional stuff. And then you can go to, in mathematics, you can go to higher dimensions. You can go up past 3 if you want to, all right? So what we're going to do with this one is we're going to verify that the point lies on the curve first of all. So I'm going to do that. So first thing we're going to do is going to plug x and y in here. You haven't seen graphs like this before, but let me just prove to you that this is on the curve. So we're going to just replace everywhere we see an x, we're going to put in a -1. And then we'll just see if the arithmetic checks on this. So we're going to have like -1 to the 4th minus -1 to the 2nd times 1 plus 1 to the 4th equals 1. Okay, let's see if that works out. Let's see. This part right here, if you take a negative number to a 4th power, that's 1. Okay, this right here would be 1 times 1, and then 1 to the 4th would be 1, right? So it looks like what you'd have is that would these two things would cancel, okay, because 1 minus 1, so that checks out. Okay, so that just means that the point -1, 1 is a point on this curve, and I just used a computer to graph that out. Okay, so what we're going to do is we're going to find an equation of the tangent line to the curve at the given point. So the thing on this is we've done equations of tangent lines. That's something we've done quite a bit. We haven't done it with implicit differentiation yet. So the thing is, when we get the answer to this problem, ultimately, you're going to have to work with that formula like we've been doing. Well, first of all, x is -1, so that's going to plug in for x1. y1 is going to be 1, so that's going to plug in like that. So that leaves us with, well, how do we find the slope of the tangent lines? And how are you going to do that? You're going to do the derivative, but the derivative you have to do implicitly, okay? So we got to do implicit differentiation on this problem. That's the whole big deal with this one then. All right, so let's work on that a little bit. All right, now I'm going to erase this stuff. Everybody okay with that? Okay, that's just arithmetic and plugging the point in. All right, let me just do that so I can have a little bit of room on here. So let's go ahead and do the implicit differentiation now. So we're going to do the derivative of the left side and the derivative of the right side. Let's see what kind of situation we get into here. Okay, all right. So what's the derivative of x to the 4th? That's just 4x to the 3rd. Do you need the dy over dx? No, variables match, okay? Next one, here's where students mess up. How do you do x squared y? Product rule. Okay, it's a product rule. And you have a minus in front, which is something you got to be super careful about. So that product rule, let's put that in a bracket so we don't mess up with that sign. So the first is x squared, the second's y. So the first, we write it down. The derivative of y, you see this all the time, is just dy over dx. Okay? Then you do it backwards. Second's y. Derivative of the first, x squared is going to be 2x. Okay? That takes care of that. That's a product rule is what I did there. First, second, derivative, like that. Okay? Then what's the derivative of y to the 4th? 4y to the 3rd, dy over dx. Okay, good. Okay? So we got 4y to the 3rd times dy over dx. For some reason I didn't put the 1 there, so that side's just 0. So this is probably not too bad. All right, so let's see what we got. So what I'm going to go ahead and do is we got to get the dy over dx's on one side, so I'm going to bring that down as 4x to the 3rd. I'm going to go ahead and just distribute that minus through the bracket. So that's minus x squared dy over dx. This is minus 2xy plus 4y to the third times dy over dx like that. Okay? So now what we need to do is these things, they need to leave them alone. Okay, they're together. And then these things right here need to be moved. So you want to go ahead and rearrange things in your head. You'll end up factoring like you usually do on these problems. Now I'm going to do it this way. It doesn't matter what order you put things in, but probably preferred that you put this one first and this one second. The only reason for that is because of the minus. It just looks better, I guess. Have something minus something's kind of a better way to write that. So I'm going to put those together like that. And then the other two things are going to move. I'm going to put the 2xy first, although the order won't make any difference. When I move that, that becomes plus. When I move the 4x to the third, that becomes minus. Okay? So I'm rearranging. Everybody good with that? Okay, just do it in your head. Okay, and what we're going to have now is we're going to factor this out. I want to go ahead and get that factored out. So that would be dy over dx, and then 4y to the third minus x squared. And this would be 2xy minus 4x to the third like that. Right, now in your head, just divide both sides by this piece there. You don't have to show that step. Okay, just divide by it. So you're going to have the derivative, dy over dx, is going to be equal to 2xy minus 4x to the third all over 4y minus x squared. Okay? All right, so we got that. That's implicit differentiation. That one's not too bad. What do you think? Okay? Yeah, as long as you keep track of everything, all right? These problems get kind of messy. So, now, what we got to do from here is, what are we doing all this mess for? Well, we got to know what the slope is. So what should I do next? I need to find the slope. All I've got is the derivative. So what I need to do is you got to go to this point and you got to plug all that mess in there. Okay? You're going to get, it's arithmetic. It's not going to be hard, but we got to do that before we plug it into the slope. Okay? So let's see. Let's be careful about this. We've got 2xy minus 4x to the third, and then the denominator is 4 times y minus x squared. All right, so x is -1. So everywhere I see an x, I'm going to put in a -1, like that, okay? And then everywhere I see a y, I'm going to plug in a 1, okay? You said you don't see anything wrong, do you? Okay. It's easy to do something wrong on these problems, too. You okay?
I heard you mention you got 4y cubed, and then you divided it over.
I can't hear anything today because I don't have my hearing aids. I just hear mud when people talk.
That 4y cubed there
Uh-huh.
became just a 4y when you divided it over.
Okay. Now that was already there. That was already
You're
on this
missing
side.
the third power.
You're missing the third
Power
power.
of 3.
The denominator on the 5.
Oh, God. Okay, let's see.
dy over dx equals 2xy minus 4x.
I know, it's not I noticed.
Already back up here.
The cube was
Okay.
after you factor.
Okay, now it's beginning to come to, look at that, okay. Third power, okay. Sorry about that.
It's just a test.
Just checking. Okay. Yeah, so that would be a third power right there. Is that it? Guess what? It wouldn't have mattered. I would have lucked out. Because I'm doing 1 to the third anyway. Okay? Very good. Okay, so now let's finish this up. So that is -2. This is going to be -4 times -1. And then the bottom is going to be 4 times 1 minus 1. Be careful with the squares and all that kind of stuff. So that looks like that's -2 plus 4 over 3. So that looks like that is 2/3 is what we end up getting on that then. Okay, then we're ready to plug in, okay, and then get our final answer. Okay, everybody okay with that? Okay. All right. So now we put the whole thing together. So what we're going to have is y minus 1, that's the y value of the point, equals the slope, 2/3, x minus -1. Now we're just going to solve that for y, and that gives us an equation of a tangent line. So that's going to be y minus 1 equals 2/3, and you can go ahead and distribute it if you want to. That thing right there is going to be a plus. So you would have 2/3 x plus 2/3. Do it that way if you want to. Okay. And then from here, I'm going to add 1 to both sides. The work's getting a little sloppy here. So we got 2/3 x plus 2/3. So what I'm going to do is move the 1 or just add 1 to both sides. But I'm going to use 3/3 like that. Just get a common denominator. You can write more steps if you need to. So this is y equals 2/3 x plus 5/3. That's a lot of work to just get to that point. That's what it is. Okay. Now, if you look at this, the other thing I wanted to kind of do, the reason I wanted to do this on a computer program is, I mean, if you look at this, let's see if that makes any sense. That's the y-intercept. That y-intercept's like 1 2/3. Slope's 2/3. Well, this is it right here. That's a 1. Does that kind of look okay? To me, it looks pretty reasonable. Okay, that thing is going to intersect somewhere a little bit bigger than 1. Up 2/3, what do you think? Yeah, it's pretty reasonable, okay? So I think it's matching that, okay? So that would be the idea. That's just a different thing that you haven't seen before. You can work with things that aren't functions. Most of the time we work with functions, but you can get away from that and work with things that look like this. Okay, you guys follow along okay? Okay. Okay. Let's do one other thing, because when you're in physics and in higher math and study, you actually do a lot of second derivatives, because a second derivative is an acceleration. It's a rate of change. It applies to a lot of different things. So we're going to do this one implicitly. I wanted to do a couple of, I'm going to do this one and then let you try a second derivative yourself. If you got that down, then you're probably beginning to get your implicit differentiation okay. All right, so we're going to start this way. You don't want to solve this for y. You just want to start differentiating. And we're going to get the, whoops, look at that. Look what I'm doing already. I'm copying something wrong. Okay, so that's 2x to the second plus y to the second, and then we're going to do the derivative of 4 like that. This one shouldn't be too bad, okay? I'm not going to give you a second derivative that's like a nightmare. I mean, it's just, try to keep that a little bit more simple. So let's do this then. So this is 4x is that derivative, okay? The derivative of y squared is 2y, and then what do you got to do? Okay, dy over dx, don't forget that, that's the key. And then this is 0, all right? Now see, what you want to do on this is you want to go ahead now and you want to get that solved for dy over dx, because we are going to do a second derivative on that. So we're going to do this like this. I'm going to go ahead and write this as 2y times dy over dx, and that's equal to negative 4x, like that, okay, because I'm just moving that to the other side. And then with this one, I can divide both sides by 2y, and then I can simplify this. So that would be dy over dx. You could reduce that down to 2, so that would be negative 2x over y like that. So that would be your first derivative. You would have that then. Okay? Okay, so that's derivative number 1. That's your first derivative. That one should be pretty basic. We've done things a lot more complicated than that. Okay, now when we do a second derivative, you got to go like this now. So go ahead and just write this down again like this. Now we're going to focus on the second derivative, which is a little more work. It's not difficult, but it's a little bit more work. So what you do is you do this. You take the derivative of both sides. So what I'm going to do on this is I'm just going to do the derivative with respect to x of both sides like that. So I'm going to do that derivative like that. Doing a derivative of a derivative, right? Okay. And then there's the notation on this. Well, the way that we haven't seen this very much, but the way that you do Leibniz notation on a second derivative is you say d2y, and then you do dx2 like that. Those are not squares. That's just the way we represent that it's a second derivative. Okay, like that. Now, how would you do this derivative? What do you think? Quotient rule. Good, right? That's a quotient. X and y are two different variables, so that's the one where we go bottom times derivative of top minus top times derivative of bottom over bottom squared. So that's what we have to apply is the quotient rule, okay? So that's going to go like this. The bottom is y. I'm going to multiply by the derivative of the top. I'm just going to write it down. Then we're going to go minus the top. The top is negative 2x. Derivative of bottom, I'm just going to write it down and put it in the formula before I do anything. Okay, then what we have is the bottom squared. Okay, so I've got bottom, derivative of top, top derivative bottom over bottom squared. Okay, now let's see what we got. So this is going to be y. What's this derivative? Negative 2. Variables match, so that's just a negative 2. Okay, we got that. Okay, it looks like we have a minus minus there, so that's going to be plus. And then how about this? What do you write there? dy over dx. That's it. That's all you can do. Okay, derivative of y is 1, but then the variables don't match, so that's dy over dx. Okay, and then this whole thing is over y to the second. Okay, like this then. Okay, now I'm going to bring this down, and this is d squared y over dx squared like this. Yes?
That 2x, or the derivative of negative 2x, is that just negative 2 or is that negative 2x?
Oh, yeah. Okay. Yeah, look at this. Okay. Look at your teacher. What is this derivative? I even asked you guys, and you said negative 2. Okay, what's that? Is that better? Okay. You guys never do anything like that, right? Never. Okay. All right. Now, here's the thing. Now, what do we do? Now, this is a lot of times where students get stuck is, okay, you're kind of used to thinking, well, I need to get this by itself. No. We've already got what the second derivative is, and we actually know what this is. If you look at all my work, you know what that is. What is that? It's that. See? So you're going to take that, and you're going to plug that in there, and then you got it. Okay? That is the first derivative. That's what it is. So plug it in, and then we'll simplify, and then we're done. Okay? So you got to go like this then. Take this thing and replace it with that. Okay? That's the thing. Sometimes that's an easy thing to forget about, but now you're ready to get the answer. So that's going to be negative 2y plus 2x times negative 2x over y. And let's see, that will be all over y squared. Okay, like that. And let's see, I'll have negative 2y. This part right here is just multiply straight across to get minus 4x to the second over y, then all over y squared like that. Now that's your derivative. What I would prefer that a student do on this is get rid of the complex fraction. I mean, that's the derivative. It's just better if you do one more step, and that last step is you would like to get rid of that y. So what I'm going to do is I'm going to multiply the top by y and the bottom by y like that. Okay, complex fraction, get rid of it. So I'm going to end up having this, and do this carefully. That's going to be negative 2y to the second. Okay, then the second thing, when you distribute, the y's are going to cross out, leaving more minus 4x to the second. And then that's going to be now over y to the third. So that would be the preferred answer. Okay, like that. Okay, that's a pretty fun problem, isn't it? Okay. I guess that's a no. I think it is. Okay. All right. So let's see. I'm going to let you guys see what you can do on this one. I'm going to give you about 5 minutes to work on this and see if you can get a second derivative on there. Okay. So let's go for it. See what you get. Application that's a little different. So to begin with this one, you're just doing a derivative on this one, and you don't do this implicitly. And the reason is it's already solved for y. So if it's already solved for y, then the approach is what we're more familiar with before this section. If you have a cube root, you can just write that as a 1/3 power. And then this is a chain rule. So this would go like this. When you're doing the derivative, okay, remember you have two functions. You have a function inside of a function. So you're going to bring down the 1/3. Like that. Okay, when you do the chain rule, leave what's inside the parentheses alone. Subtract 1 from the exponent. You can do that in your head if you want to. So I'm going to subtract 1, and then I'm going to multiply by the derivative of what's inside. Now you can just do that in your head if you want to. The derivative of what's inside is 2x, and then the derivative of minus x is 1. Derivative of 1 is 0. Okay, so that's really your derivative. So you would have 1/3 x squared minus x plus 1 to the negative 2/3 power times 2x minus 1. You're not doing that implicitly because it's solved for y. Okay? Everybody follow that? Okay, I'm going to simplify it, but that's pretty simple. Okay, that came from the derivative of what's inside. Remember when you're doing the chain rule, you also have to multiply by the derivative of the function that's inside, because you have a function inside of a function, like we talked about on the chain rule. So that thing becomes, that derivative is right there. Okay? That's what we talked about in the previous section. All right? All right? Now, what we want to do from here is that's a negative exponent, so it's a good idea to go ahead and bring that down to the bottom. So I'm going to have like just a 3 down in the bottom. And then this whole thing is going to become x to the second minus x plus 1 to the 2/3 power like that. Okay? Then you can change it back into a cube root. I'm going to go ahead and do that. So that's going to give 2x minus 1. And then we have cube root of x to the second minus x plus 1 to the second like that. And then that trinomial doesn't factor, so that would be as far as we take that. Okay? So I want to make sure everybody's kind of on track with that, because the chain rule is what you're going to be working on, or homework on, mostly over the weekend. So where does that come from? Remember, when you do the power rule, you also got to multiply by the derivative of what's inside. So 2x minus 1 is that derivative. That's the chain rule. Okay, you got that? Okay? All right. Okay, on this last page up here, this is something that you might encounter in higher math. You see this actually a little bit in Calculus 3 and differential equations, and in physics, the idea of what an orthogonal trajectory is. So I just wanted to do something a little bit different. This has to do with implicit differentiation. And let me show you what the idea is. Now what I did on this one, I just took a computer program and I drew some curves on this. This thing right here is a cubic function. And cubic functions, if you took college algebra recently, you may remember cubic functions kind of look like that, don't they? Okay, they have that. Now that a is going to vary. Okay, as a changes, that thing just stretches and shrinks. Okay, so as a gets bigger, then that cubic function just kind of stretches more like that, and so forth. Okay, this one right here is an ellipse. Okay, a lot of times students don't know their conic sections very well, because in college algebra we just barely lightly cover it at CCD. So that's an ellipse, which is just like an elongated circle, kind of like that. Okay, so what I've done on this is b varies, and as b varies, it just makes the ellipse kind of change, elongate, stretch, and shrink, kind of like that. So if you look at my graph that I put there, there's some ellipses, and then there's some cubic functions. Okay, so trajectories generally is just like in physics, is the path that something is following. So you could have something that does an elliptical path. Of course, that's what Earth does. As we revolve around the sun, we go in elliptical paths. All the planets go in elliptical paths, not circular paths. We know that That was proven by Kepler back in the 1600s. So, and then you can have things that follow cubic paths also. So the idea of an orthogonal is just a word we use that's the same really as perpendicular. They're at right angles to each other. The trajectories can be at right angles to each other. And what I'm going to do is I'm just going to show mathematically that this cubic is at a right angle to this ellipse. Okay, and this is something we're going to do with differentiation. So what we're going to do on this is we're going to show that the families of curves are orthogonal trajectories of each other. So what we're going to do is we're going to look at the tangent lines are perpendicular. And it's not the trajectories. The idea would be something like this. This is a little hard to see on my diagram here, but the idea would be like this. I'll just pick this point and tell me if this makes sense. That would be like a tangent line to the ellipse, right? If you did a tangent line to this cubic, it kind of looks perpendicular, right? Kind of, all right? So the idea on this is no matter where you are, if you pick a point on the ellipse, you should be perpendicular to the tangent line on the cubic. So what we're going to do is we're going to show that and demonstrate that. Okay, we're going to do this with just some calculus and do some derivatives. And this will probably make sense to you because you remember hopefully a little bit about perpendicular lines. So what we're going to do is we're going to go ahead and do the derivative of this function. Okay, this one you don't have to do implicit differentiation. We just got dy over dx. If you did this derivative, what would that be? You can do that in your head. 3ax to the second, right? Okay, a is a constant. So you just bring that down like that. That's it. Okay. Now when we go to this one, what we're going to do is this. We have to do this implicitly. So we're going to do implicit differentiation on this. And then we'll kind of see what we have. We're going to try to see that after we differentiate, we want to see if we can figure out why they're perpendicular to each other. That's what orthogonal means. Okay, so let's do this. This is a super easy implicit differentiation. That's 2x. Okay, what's the second one going to be? 6y times dy over dx. Good. Okay. And then what's the derivative of b? 0. That's a constant. B is a constant. That's not a variable. So that's going to give you 0 like that. Okay? Now what we're going to do is we're going to solve this for dy over dx. So I'm going to move the 2x the other side. So we'll have 6y times dy over dx equals negative 2x, like that. Then I can divide by 6y. Okay, and then let's see what we have and see what we come up with here. So that's dy over dx. Now if you reduce this fraction, that reduces to negative 1/3 times x over y like that. Now you can just write it as negative x over 3y if you want to. But I want to see if you guys notice anything on this and see how observant you are. Okay? Do you notice any reason why those things might be perpendicular to each other from your background?
Because it's a negative reciprocal.
Good, yeah, it's a negative reciprocal. Good, okay. You probably learned somewhere in college algebra or something, did you guys learn that if you had like a line, say for instance you had 2/3 x is one line, and negative 3/2 x is the other line, aren't they perpendicular? Okay, and the reason is because of the slopes. So what's happening on this is, if you put that over 1, see that slope is 3 over 1. The slope over here is negative 1/3. Okay, so they're perpendicular to each other. Okay, so that just means that these trajectories, their rates of change are going to be following at right angles to each other. So we would say the curves are orthogonal. You may have never heard that word before. You'll learn a lot about that in Calc 3 if you're going to take that class, because you start learning about vectors in Calc 3 in physics. Okay, so that's the idea. That's just something a little bit different. Does that make sense?
How come in the first one we do dy over dx and not d over dx?
Oh, what I did is I wasn't doing this implicitly. Okay, it's already solved for y. So if it's already solved for y, you just do the derivative the way that you're used to doing that. So we are doing the derivative of y with respect to x. Okay, right? See, like on this one, I did that implicitly. That's why I did d dx. That's showing that I'm doing the derivative of both sides, and then since there's a mixture of variables, I introduce the dy over dx here when the variables don't match. That's the difference. Okay, all right? Okay, so let me close that off, and then we're going to start the next section.